Welcome to Web Handling. My name is Dave Roysum. I am very excited to continue this series on the economics of web handling. In this clip, we will show you why waste can be a good thing. In this specific example, we will use economics to determine the optimum level of waste at the bottom of a wound roll. The viewer is urged to watch the previous clips Web20156c and especially 56b so that we don't have to repeat novel concepts that were introduced there. This example is one of a half-dozen successful case histories that used economic analysis to find the economic optimum setting for a web machine. Others are described in what may be the most important paper I've ever given to date. Tapia also must have thought so because it was a keynote address at one of their conferences and was also presented at two other international venues that same year. Returning to the problem at hand, management tasked us with a problem. Task is like ask, except for it's not really a request. In any case, the assignment was to reduce waste at the bottom of their large jumbo rolls. That waste is shown in red just above the core. Those familiar with the paper industry will know that this waste is expensive. That 2 inches left on the spool will cost about $2 million per year per high-capacity machine. Those familiar with the paper industry know that 2 inches is about the industry norm for most grades and most machines of this type. To complete the bigger picture, the jumbo rolls made on the paper machine would next go to an offline coder. Paper coders can be quite fussy. Fussiness can also be the case with other webs and other web machines and other web customers. While reducing waste may seem quite reasonable, there are many problems with this assignment. First, reducing waste itself is trivial. It is merely a setting on the next unwind. There must be something standing in the way, otherwise this paper mill and every other paper mill would have done it already. As I teach in my problem-solving classes, the number one problem is number one for very good reasons, and you had better truly understand what those reasons are. One of those reasons is that waste is also a good thing. As we will see, it protects the downstream customer from even worse troubles. Thus, to assume waste is purely bad is a crippling oversight. This is why some popular management programs, such as Zero Defects, can be economic nonsense. They do not consider that waste can, and is quite likely, a good thing too. Waste in moderation can protect you from even worse troubles. These and many other limitations with popular management programs will just make it that much harder to understand the problem and thus make good economic choices. So first, let us acknowledge that there is a kernel of truth to the waste is bad myth. Here it is trivial to cost as core waste as a function of the variable to study. In this case, the amount left on the core or spool. In the paper industry, it is very approximately $1 million per inch per year per machine. So, if all you considered was the badness of waste, you would come to the conclusion that the optimum amount of waste is 0. This is clearly an absurd answer because no one in the paper industry is running at 0. There are reasons why, and you will never understand the system unless you also consider with equal weight the goodness of waste. As any operator will tell you, running the unwind down to the last wrap on this kind of machine is not only a bad idea, it won't work at all. The reason is simple. The material is damaged near the core. We learn why this material may be damaged by the winder and the unwind in my Web 101 classes, and sometimes it is due to unavoidable factors such as gravity. The outcome of this case is predictable: more web breaks and other issues near the core. Thus, to understand the system and make the wisest economic choices for settings, we need to understand the goodness of waste near the core. Here, we can do an extended trial of different diameter settings for the turnup and tabulate waste. If a typical value is 2 inches, we may also try 1 inch, and then 3 inches. Additionally, we saw in the last clip, we may get another data point for free. That is, the cost curve must be concave upward, going to infinity on one side. You simply can't run zero waste on this kind of machine. Web break rate is easily converted to dollars. The worth of this machine is approximately $20,000 per hour, and a web break on this machine takes the machine down for about 1/2 hour. Thus, a single web break on this machine will cost about $10,000. Note, however, that the true cost may actually be higher than these simple estimates because this machine, a coder, does not immediately reach equilibrium when it starts up. So the first half hour after start is more risky for waste and delay. Finally, note that if you are in the converting industry, your rates may be 1/10 of that discussed here, but the principles are identical. In any case, we fit a curve to those 4 data points, 2 being trials, 1 being normal operation, and 1 being free. We can now see the costs of running too close to the core. Note, however, that this curve will not go to 0, even with generous padding near the core. The reason is that there are other ways to have web breaks besides having damaged the material down near the core on the upstream winder or unwind. The asymptote is the base web break rate that does not have to do with damage near the core. Now we can assemble the cost curves for both the goodness and the badness of core waste and sum the two. The total cost has a minima, and that is the economic best for this situation. Interestingly, the analysis gave a minima of about 1.5 inches instead of the more typical 2-inch practice. However, as you see, the curve is quite steep on the left side. That means that to be conservative, knowing the uncertainties of the study, you should bias your settings a bit towards the right. This is because it is much more flat to the right, in other words, safer. Thus, the optimum may well be the 2-inch norm that management told us is not good enough. None of this should be too surprising. All we have done is use economics instead of making assumptions and guessing to get the best answers. None of this should be too surprising. We see trade-offs like this every single day. Internal rejection protects the end-use customer and thus ideally reduces claims. The same is true of trim removal. It also protects you from internal rejection and customer claims. Roll size is a trade-off between inefficiencies of small rolls versus waste at the top and the bottom due to damage from the winder or unwind caused by gravity and nips. Come to my Web 101 class to learn about those details. Finally, when we take a machine down for repair, we are ideally trading downtime against even higher waste and customer complaints by running a limping machine. As we've seen, and as we come to expect, waste is both good and bad at the same time. However, to think that this example is about paper or coders or flying splices or web breaks is to miss the big picture. These principles are nearly universal. And so, what do we do when best is not good enough? What do we do when the best in the industry is not good enough? Well, stay tuned. In episode 201.56f, we will answer that. In the meantime, we have a couple more examples and a couple more analysis tools to cover. Please stay tuned.